So now let's think a little bit about how M sub R looks for a general ring. Well, I already said that this, with R coefficients, is just the Z coefficient 1 tensored with R. So this tells us that M sub R can be written as a union over all the elements of R of M sub little r for an element where, so these little MRs are like these sheets we had, but they were separate. They were separated for the integers. So this is plus or minus mu x, where mu x is a generator with z coefficients, and then we've just tensored that with our element r. Now, again, we can analyze what all the sheets look like. If so, MR just is a copy of M if our element R is equal to minus R. So, for example, if R has order 2, or if R is 0, then we just get a copy of M at height little r.
Can I ask a really stupid question?
Yeah, go for it.
That property of there, is that general attribute of epistemology?
Which property? The first line?
Or is that just for these orientations?
No, that's just that's a general property of having R coefficients. Okay. So if this holds for little r, then we just get a copy of M at height r. And otherwise, we get a copy of the orientation double cover. So these are the two cases we get. We can draw an immediate corollary from this. If M is Z orientable, then M is also R orientable for any R. Well, why is this? I was very careful to specify that my ring had an identity. So you can just look at the section given by the Z orientation and tensor that with 1, and that gives you an R orientation. So this is because 1 is in our ring, so we take Z orientation tensor 1. This is the first corollary. Secondly, what if M is not Z orientable? Well, if M is not Z orientable, in a moment I'll drop the use of the Z, and I'll say that if I say orientable, I mean with Z coefficients. So if it's not orientable, but it does happen to have one of these elements, which is, let's say, so I should have said if R is of order 2, so we exclude the case R is 0. It's of order 2, which implies this. So if M's not orientable, but it does have, has an element of order 2, then that element gives us an orientation, because at height r for that element we just get two disjoint copies of M. We can take a section, that gives us an R orientation. Then M is R orientable. So we use a section at height r. And then just now a simple observation following from this, Z mod 2 has an element of order 2, so automatically any manifold is Z mod 2 orientable. So, following from those three comments, really the most important rings that we consider are the integers and Z mod 2. If we have Z orientability, this tells us about all the other rings, and we know that we automatically have Z mod 2 orientability. So this is important as well. Okay, so if M is closed and R orientable, then map from homology of M, M in the top dimension, to all these local homology groups. This is an isomorphism for all points in M. Well, we kind of said that it's R orientable if we can combine all these local orientations to give us something global, which then restricts to give the local orientations over each point. So this is kind of, this is not saying a huge amount, but a remark about this. Well, we need to be careful that M is closed so that we get something compact when we put all these orientations together. In order to get a cycle in HM, we require this to be closed. And then when we have a class here which does map to all these local generators, we call that a fundamental class. So an element, I'm going to use square brackets M to denote my fundamental classes. Well, it's a fundamental class for M with R coefficients. And so by the theorem above, if M is closed and R orientable, then we have shown existence of a fundamental class. We can always find one. So M closed, R orientable implies there exists a fundamental class. Now, I'm going to give an idea of what a fundamental class looks like in the case of simplish or complex. So just briefly, suppose that M has the structure of a simplish or complex. Then, well, M is a class in top homology, so it's just a linear combination of M simplices. And, well, let's just think about Z coefficients for a moment. For this fundamental class to map to plus or minus 1 in these local homology groups, for all x, if we in particular consider a point in a simplex interior, on the interior of one of these m-dimensional simplices, this tells us that our coefficients have to be plus or minus 1 for all of these simplices. So, and also we want this to be a closed cycle. So we know when there's a simplex next to another simplex, if we've chosen a sign here, say plus 1, then we need to, this determines the sign of the neighbouring one, in order that the boundary maps cancel along their intersection. So a choice of ki determines neighbouring coefficients, kj, say. And so, if we're a choice of sign such that this is a cycle is only possible if M is orientable. So yeah, an orientation here is a consistent choice of plus or minus 1 associated to each simplex in such a way that you get a cycle. And also note, in particular, if we're only working now with Z mod 2 coefficients, whatever our choice of plus minus 1 is, it's the same, so we don't have to worry, and we automatically get an orientation for just summing all of the top dimensional simplices. So with Z mod 2 coefficients, so with just 1 for each, is a fundamental class automatically. Well, a Z mod 2 fundamental class.